Okay, thanks a lot. Thanks a lot for inviting me. It's really great to be here. It's my first time here in Serbia, and I really enjoy it. So my talk today is going to be about causal discovery, and you will notice that there is some overlap with some of the other talks. I have bar plots in there, and I will talk about logic and about statistics. I will, of course, talk about causality, because that's the topic. I will talk about big data. I will talk about, well, many different things. It's a bit high level, but I hope to show you also something about the type of models and the type of algorithms that we're going to apply. So this is going to be the outline. What's causal discovery? Our own approach to that, which is actually based on a bit of logic. We'll do a Bayesian approach. I will show you some applications if I have time, and hopefully I can say you a bit more about our current research and what we think should be the future goals of the field. Okay, introduction. So we can read many times in many newspapers and well, basically everywhere and medical journals, we have discovered some kind of link between something and something else, right? So here is the famous hockey stick. So climate change. But what's exactly causing climate change, right? That's what we'd like to know. Let me go to this example. So here, this is a picture of the decline in violence by juveniles on the street, combined with the advent of violent video games. And some people claim that there is a cause-effect relationship. So because we now have more violent video games, the young people don't have to go out on the street to really exercise the violence over there. So it's a good thing to have violent video games. I don't know, but we should try and understand it, right? So here is a medical example. So what you can see over time is that the incidence of throat cancer in Great Britain is really stable for females, but increases for males. Do we have any idea what's going on here? Well, we probably don't, but we're interested in kind of cause-effect relationships. Okay, so this was what we talked about earlier this morning, smoking and lung cancer, right? So you can look at different countries, you can look at tobacco consumption in different countries, and then the number of incidents of lung cancer, and you find some kind of correlation. And we understand what's going on. So there's a clear correlation, but we also have some theory that might explain that there is some cause-effect relationship here, right? So smoking causing lung cancer. Well, I don't know who's seen this one. Chocolates and Nobel Prizes. So who's seen this one before? Okay, so some of you have seen it. So what you can see here on the axis is chocolate consumption. So think about chocolate and, well, smoking. And then Nobel Prizes. So think about lung cancer and Nobel Prizes. And you can see that the correlation is a lot stronger here. It's 0.9. I think in the other case it was like 0.6. So the link is stronger, and there was really a paper on this, right? And trying to hammer down the point that correlation is not causation. And the Nobel Prize winners, they made jokes about this. They said, yeah, we indeed eat a lot of chocolate. And so that's why we got these Nobel Prizes. Well, we all know that cannot be the case, right? So that's probably not the case. So is there anything else that you find striking in this graph? Anything? Come on, you should see this. Well, there's clearly a home advantage here for Sweden. So they eat quite a lot of chocolate, but they get many more Nobel Prizes. And I'm not sure if there are Germans in the room, but you should probably eat a bit less chocolate or win more Nobel Prizes. So you can choose, probably. Okay, so here is, well, it's not an actual example because I don't have a database on this, but you can think about it, right? So what happens if you would gather data on car accidents? Well, what you will find, if you will look at correlations, that there is a very strong correlation between braking and getting into an accident, which probably means that we shouldn't brake, right? Because it makes no sense, because if you start braking, then, well, you will run into an accident, so please don't, right? Of course, it's not the case, right? So we observe in correlations, a strong positive correlation between braking heavily and car crashes, but we don't care, right? It's not what we should be interested in. So the correlations describe the world as we see it, but what we're interested in, and yesterday afternoon we talked a lot about policies, we are interested in what happens if we intervene, if we make new policies. And what happens then, right? So that's why we should be interested in causal inference, in causal discovery, and not so much in correlational analysis. And when we think about these different areas, these different problems, we can think about models behind them, right? And I draw here what you could call Bayesian networks or structural equation models or whatever, but some kind of graphical representation. And then you can understand why in some cases you find a positive correlation, but maybe a negative causal effect, right? So, for example, in this case, there's clearly a negative causal effect between braking and crashing, but because there is a common confounder here, like something like danger or maybe slippery road or whatever, if I look at the correlations that result from this graph, they will be positive, right? And same thing probably here, if we look at the chocolate, well, I don't think there is a direct causal relationship between chocolate and Nobel Prizes, but there's something going on probably with wealth of a country and things like that, right? So if you're very rich, you probably can spend a lot of money on science, but you can also eat a lot of chocolate because you can afford that, right? So that's hopefully, I guess, what's going on. So we can make these kind of models, we can try to understand them. Okay, so I hope I've convinced you that we should try, right, to find causal relationships from observational data. But then there are these sayings, right? So people tend to say a lot, correlation does not imply causation. We really like that. This is a nice graph from Daniel Engber, who looked at Google Trend data, and there was a sharp increase, as you can see, in these kind of statements in books in this case. Right, so we love to say that. This is what Nello already alluded to. So there was this popular book on big data. I think it's still the most popular one. They have a whole chapter on causality, and they make statements like, we shouldn't care anymore about knowing why, but only about knowing what. Here is the end of theory. If I understood it correctly, he retracted that statement later, which is good for him because I think it's bogus. Right? So it's not what we should be looking at. Correlations are kind of nice, but they're not really useful. So the logical reasoning that people seem to follow is that correlation does not imply causation, so it's impossible to discover causal relationship from purely observational data. Well, this really is a fallacy. And the reason that it's a fallacy is because we always think about these pairwise correlations, right? When we think about the pairwise correlation between chocolate consumption and Nobel Prizes, well, of course, you give me a number, 0.6, 0.9, it's completely symmetric. Yeah, of course I cannot say anything about the direction if you give me a number which by definition is symmetric. However, if you give me more information, and it can be more information about two variables, I will give you an example in a moment, hopefully, or I give you more variables and I tell you something about conditional independencies and things like that, well, you can try at least. And you can say, well, I don't buy it, but then, well, quite a lot of statistics you can throw out of the window because you always have to make assumptions. So also, if you want to do causal inference, you will have to make assumptions. But that holds for any statistical model that you're going to apply to your data, right? So don't be so afraid of that, I would say. Okay, so here's an example. This is not the example, so not the type of algorithm that I will be talking mostly about, but it might be insightful. So this is on pairs of information. So if I would give you the correlation coefficient, well, you couldn't say anything, of course. But now I give you the data. So this is the data, so this is x and y, and this is y and x, but actually it's the same data. I just rotated the plot for you so that you can look at it. And I'm going to give you the information that either x causes y or y causes x. And now you can choose. Okay? So well, you can design an algorithm, and then the algorithm has to choose. So who thinks that it's x causes y? Who thinks that y causes x? Y causes x. Who thinks that, well, you can tell me anything you like, but there's no way we can say anything about this? Okay, good. There are some people there. And the rest is sleeping. So you get the question? So is it x causes y or y causes x? So if you would have to choose, right? So it's a gamble, and you would have to choose. And I'll give you €5 if you give the right answer. So what would you choose? Y causes x? X causes y? Anyone? No one? I would go for x causes y, to be honest. Okay, so my explanation for this is on this slide, so maybe we can have a look at that. So if I say that x is kind of the input variable and y is the output variable, then this data is relatively easy to explain, because I can just say, well, y is just a linear model of x and there is additive noise. Well, we tend to like these kind of models. We think they are kind of simple models, right? Okay. Now, try to come up with a model where you say that x is a function of y plus noise. Well, you have to come up with some pretty complicated noise model to explain what's going on here at the boundaries. And you can say, well, I'm willing to do that. Of course, it's perfectly fine. I'm not saying for certain that it's going to be x causing y. I'm also not saying for certain that it's going to be y causing x. But we tend to use Occam's razor all the time, right? So we like simple models. And I would argue that this is kind of a simple model. And this, well, it's going to be a pretty complicated model if you want to explain your data with that particular kind of model. Okay? So there were competitions on that. A particular group in Tübingen, they gathered like 100 different cause-effect pairs, where you could argue then, well, what's the cause, what's the effect? And then they have gaggle competitions on that, right? So we're not perfect on that. I think on average, people do like 80% correct. I think this is a nice example. So this is altitude in Germany for different weather stations, and this is temperature. And, well, apparently it's easier to model it in this way, right? So then well, it's kind of a bit noisy, but the other way around, it's more difficult to model. So I don't know. And so most of the algorithms that people apply will say that altitudes kind of causes temperature, in the sense that if you put a weather station higher up the mountain, it's probably going to get colder. It's not that when it gets colder, it will fly up or something like that, right? So that's why we talk about cause effect here. Okay, so this is trying to convince you, but I'm not sure if I managed, that there is more information in data than just the correlation coefficient, and that you can use that information, so in this case kind of higher order statistic you could say, to try and say something about causal direction, even though it's purely observational. So I didn't do any intervention studies. I don't have treatment or non-treatment or things like that, right? So, and still we can try. So what I will be talking about in the rest of this talk is more what can we do when we have more variables. So not the pairwise case, when we have two variables and we have to look at higher order statistics, but more than two variables, and then can we say something even just looking at the correlation matrix, but then saying more about independencies, dependencies, conditional independencies, and things like that, right? And I think one of the first papers trying to do that is a paper from like 12 years ago in Science on protein signaling networks. Well, lots of information about proteins, all kinds of experiments, also some intervention experiments, and try to find what the causal effect is between different proteins. Okay, so how am I going to do that? So this part is going to be slightly more technical. So we need a language, right? So if we want to talk about causality, we need a language for that. And the language that most people use are structural equation models in one way or the other. And it goes back to Wright, to past models, or so Pearl made them pretty popular in more recent years. So what do we do? Well, we think that we can describe the world with a model that looks a bit like this, where we have, you could say, the effect variable, we have some direct causes, we may have some noise, and there is some causal mechanism, right? So that's the assumption. So we assume that we can describe the world with models like this, okay? And you can say, well, my world doesn't look like that. Yeah, fine. But what we then also have to assume is that there is some joint probability distribution on the noise variables that we cannot observe. But this, at the end of the day, induces a joint probability distribution on the observed variables. Right? So if this is my causal model, I assume something about the joint probability distribution, then I get a probability distribution on the variables that I can observe. So we tend to think about these as graphical models and maybe Bayesian networks, so then we can draw these kind of graphs. So we typically don't really indicate these noise variables there and only look at the observed variables. We can read off the causal structure here. So X1 is a parent of X3. So if we interpret this as a causal model, so Bayesian networks you don't have to interpret as a causal model, but suppose I tell you this is a causal model, then there is a direct causal effect in this model from x1 to x3. And then you can write down these structural equation models, right? So this is the type of model that people even use quite a lot in, I think, in sociology, psychology, medical science. They try to write down these models, basically, right? Okay. So what's nice is there is a way to compute the effect of interventions in these kind of models, in structural equation models. And Pearl invented the do calculus for that. So we can make the distinction between observing and intervening, which I think is very important, right? So in his notation, he calls that do. So you set a particular variable to a particular value, okay? And so what happens there, if I apply a do operation on a particular variable, then the other parents, they don't really matter anymore, so you basically cut those arcs, you could say, and there will be only this effect on this particular variable. The important notion here is, so there is this calculus, which I think is really nice, right? So you can, well, not always, but you can, in many cases, make these calculations. But the important thing to realize here is that doing something is not the same as observing something, right? So if I intervene, so if I set this particular variable to a particular value, it's completely different from just letting the system run and then observing that particular variable has a particular value, right? But even if you have this model and you've learned this model, in some cases you can reason about this. So you can do calculations, and the do calculus is meant for that tell you what the effect of a particular intervention of a manipulation is going to be. So an example of that is you want to predict the effect, as we discussed this morning, of the treatment for an individual patient, right? So that's a typical intervention question. So that's why we have this notion of counterfactuals and things like that. So you don't have the information, you didn't observe it, but you would still like to reason about that. And in these kind of models, people typically assume that there is a known structure, and often they also assume that there are no confounders, so there's no latent variable. So in case of chocolate and Nobel Prizes, there is no wells, or if there's wells, you should really measure that, right? And then you can do these types of calculations in those particular cases. Well, the point is, in practice, and then this is basically what we get. So we get reliability statements on there being a causal effect between two different variables, okay? And then we can translate that to a model, because they would like to see models, and then you get something like this. So we published this 2 years ago, and we tried to relate it to what other people found in literature. So some of the links we are pretty certain about, other ones we are not so certain about, right? Whether there's really a link here, I don't know. Based on the data that we have, we just cannot make that statement. But what we do see that if there's a link between the gene and the activation, then it's probably going to be an indirect link and not really a direct link. So that might help explain why in some studies they can find it and in some studies they cannot find it. Here's another example from a more recent paper, I think it came out last month, where we looked at the comorbidity between autism and ADHD. So there is a large data set, well, a bit large data set, and we applied a similar analysis as we did before, and then we show this to basically the psychiatrist, not claiming that this is the model, because this is not the model, but trying to tell them that if they want to come up with another randomized control trial, then maybe look at this model and see where you have a chance to find something there in terms of a cause-effect relationship, right? So that's the way that we ourselves at this point in time try to look at these types of models. And we can say, well, there seems to be no relationship between, for example, age and impulsivity, but only through hyperactivity, for example. There's one interesting notion that we find in all these data sets that we tried so far, and we've also published that. I didn't put it on the slide. But we always find this link, well, here it's not so clear because we don't know, but between DAT1 inattention and hyperactivity, that hyperactivity is conditionally independent of DAT1, for example, given inattention. And we also have DAT1 probably here with gender. So gender, inattention, hyperactivity. So inattention is kind of mediating between gender or some risk haplotype and hyperactivity. And that gives us reason to believe that inattention is more important than hyperactivity in ADHD. Okay. a bit about current research goals and ongoing research that we do in this area. So I didn't really talk about big data, so I did have it in the title. And the reason that I also put the question mark there is because I think it's really difficult to do causal discovery on big data for two reasons. So one reason is that big data typically have many variables. Okay, we got that, right? So if you have many variables, things get difficult. But also if you have a lot of data. And that I find the more interesting problem, and I will get to that. So we have an ongoing grant with Aad van der Vaart, who is one of the major statisticians in Europe on that. So the first thing about big data, suppose you have many, many different variables. So there is this statement that learning Bayesian networks on many variables is an NP-hard problem. So you would say, well, then the same applies to causal models. Luckily, it's not. So that might help us a bit. So, and we feel that it's because of this kind of local relationship in causal models, it gives you people, we want to give them what's cause and what's effect, right? We're definitely not there yet. And it's a pretty long way to go, perhaps, but we have to work towards that. So we have to work towards software implementations and to connect to Natasha's talk. So we should have some kind of way to report our results in terms of causal confidence measures. We don't really have them yet. Well, we have Cohen's D, it's what some people sometimes use, but we should do better than that. So there's definitely a long way to go there. So I had some negative statements at the beginning about causality and big data. Luckily, I could find with a bit of work a more positive statement. So this is from Jeff Hammerbecker, and I think he's right. So we cannot use correlation analysis to make complex models of the world because everything is correlated with everything else, right? So we have to search for causal relationship because there we can not only have our interventions but also hopefully have simpler models. Because if I have a causal model on a few variables, it will make everything dependent of each other, and we'll find many, many correlations, but it doesn't tell me anything about the underlying structure. Right? So that's what we have to do. Okay, so take-home message. Well, we've seen this one, and then we could do our causal discovery on that, and then this is what we can infer. So we can say, okay, if I have chocolate and Nobel Prizes, then there is no way I can tell anything about the cause-effect relationship, and that's basically saying correlation does not imply causation, and you're perfectly right. Correlation, a simple correlation between two variables, does not say anything about the causal direction, right? And it's obvious, I would say. So this, to me, is really boring. So you should keep saying that, and it's fine. But the more interesting part is that if you can assume that there is some unknown underlying model, then you observe data, you can try and infer the underlying causal model. And you can make causal statements. Of course, you have to make assumptions, no doubt about that. But there are many opportunities there in this area, as others showed as well. And so I think this is cool and is what we have to work on. Thank you very much.
Okay, questions?
Thank you. So thank you for a wonderful talk. I want to ask you, are you able to come up with any confidence estimates associated with this sequential learning of the causal graph? As you are getting more data, improving your confidence potentially about the graph indeed being one way or another?
Yeah, we would love to, but it's not easy, right? So what we try to do is to come up with a way, which already is very difficult, but some others do as well. Let me see if I can find it. Yeah, so for example, to find a way to attach a probability to a statement like this. Once we have that, even then it's not so easy because then I have to combine a statement like this and a statement like this. I have two probabilities. How do I combine them? There you can use bounds at least, and that's what we're trying to do. But the risk is that the bounds get very wide. So that's a bit of, yeah, that's the issue. And we cannot assume that these are independent because they are clearly dependent statements derived from the same data. So it's quite a challenge there. But for relatively small models, well, the bounds don't become extremely wide yet, so then it's okay. But it's clearly a challenge. But it's the way we have to do, right? So we have to come up with probability. Well, like you said this morning, we have to not just say this is the model, but we have to say something about how certain we are that this is, in fact, given the data that we have, the case. Yeah.
Okay, if no other question, let's thank Tom again.